All right, let's get started. Okay, so on last Thursday we were talking about a new type of clustering other than k-means, something that we called mixture of Gaussian. So I kind of conflated mixture of Gaussian clustering with EM last week. So I wanted to just make sure that this was clear. So when we talk about clustering, we're talking about mixtures of Gaussians. This is something where it's going to look like you'll have, points that you're going to try to cluster. And they'll have some multivariate normal, which in our case we're restricting it to no covariance and a unit variance, so they're going to be circles with the same size. You have then the only things you need to learn are where the items are, so the centers of the Gaussians, basically. And then you have a mixing probability. The mixing probability is this pi, 1 to k, and that basically says what proportion of data is in each cluster. So even though we're using sort of a unit variance, meaning that all the clusters are essentially the same size, because we have this mixing probability, some of the clusters can actually have more points and could be kind of a little more spread out. So you might have a cluster, say this cluster, where it grabs more points around the circle, even some that might be getting close to the other ones. These might fall in to this cluster, even though they might be closer to the center of this cluster, of this other cluster. So the means and the mixing probabilities are what define what the clusters are and kind of define the size of the clusters. Now, to find the means and the mixing probabilities, we have to have some sort of method. There's no way to directly determine these sort of analytically, so we need to use some sort of procedure to find these, or at least to find some approximate solution that fits the data well. That's where expectation maximization comes in. So expectation maximization that we're talking about, commonly just called EM, that was a technique that allows us to solve this particular problem. EM applies to a lot of different problems. Anything that can be formulated with a hidden variable, which we'll talk about and review in a second, but anything that can be formulated with a hidden variable to make the probabilistic formulation much easier can use EM to essentially, you add a hidden variable into the probabilistic formulation, and then you marginalize that hidden variable out by essentially looking at every combination of that hidden variable and what it would do to the probabilistic formalization. So it is it's a very common technique in statistics when you talk about probabilities and anything with hidden variables. And you shouldn't conflate it with the clustering, even though I'll often, during this class, will often say EM when I mean solving a mixture of Gaussians with EM. You need to sort of be clear that these are two different things. One is a clustering technique. The other one is how you solve that clustering technique. Okay, so we talked about how EM uses a hidden variable. A hidden variable is just something, it's a random variable you don't know. It's not really intrinsic to the problem in and of itself. But if you knew that hidden variable, you can solve for the parameters you need. So in our case, if we knew, if delta was assignment to clusters, essentially if we knew which cluster each data point was in, then we can solve for the parameters very easily. Because if we know the location of the data points in the clusters, then it's just a matter of doing the super simple mean, basically. Let's see, this is mean of points in J. The means can just be found by averaging over all the points that you know are in J, again, defined by that hidden variable. And then the mixing probabilities are just going to be the number of points in J over number of points. So again, that's just the fraction of points that are in a cluster to determine what the mixing probability is. Now, like I said, if we know delta, those two things are easy. Now, of course, we don't know delta. If we knew delta, we had the problem solved already. So this is where EM comes in, where we're going to take the expectation over all possible delta settings and determine these parameters by taking that the expectation over delta. The EM is going to be an iterative process. It's going to seem like it's much like a k-means, where you're going to sort of assign points to a certain place, figure out the means and the mixing probabilities, then maximize the layout of those particular parameters. So you're going to go from a setting of parameters, and then you're going to update them each time. So let's go back to looking at the formulas. This will mostly be formulas today. Hopefully it won't take too long. I've tried to simplify these formulas. There's much more detail in the book. It's often not very productive to look at all the formulas for most of the people here, so I'm trying to just rough it out so you guys understand how, if you encountered a new EM, how this stuff kind of goes together. So here are the formulas. You have two things. You have a Q function. This is a function of your parameters given your existing estimate and the data. That is just going to be the expectation over all possible settings of delta of some loss function. Now, the loss function is going to depend on the application, so we're going to have a specific one for mixtures of Gaussians. But if we knew this, or sorry, let's just fill out this formula. So if we can write out the expectation, that's just the sum of the loss over the parameters times the probability of, let me get this right. I went over my notes this morning, and I found that I had about 4 major mistakes in them. So hopefully I've fixed all those. So it's just this is just the definition of expectation. So we take the sum over all possible settings of delta of the loss times the probability of that delta setting given the current parameters. So once we get the Q function, we have the second step. This is called the expectation function, or expectation step. And again, it's because we're taking the expectation over the hidden parameters. Then we have the maximization step. And this is just saying that we're going to take the current Q function, and we're going to derive the next set of parameters by finding the best ones given the current Q function. So argmax of theta of the Q function, that's not a Q function, Q function of theta given current theta and x. So we're going to form this Q function, and then we're going to maximize, find the maximum of the parameters. We'll just iterate back and forth until we've converged to some point where the centers aren't moving around and the mixing functions aren't moving around. And this will work in a lot of different areas, but we'll look at now the math for mixture of Gaussians. So this is specifically for, I'm going to need this particular formula again. So this is specifically for Gaussian mixture models is typically what they're called. So the things that we're going to need, first we're going to define, well, first let me just write out some of the things we know about the different probabilistic formulations here. So this is stuff that will all be needed in a second. I'm going to try to label the equations so that you guys kind of know which equation is going into where. So this is going to be equation 1. This is going to be equation 2, just the E and the M step. And now, move these over here. This is equation 3. And this is just the probability of a point given which cluster it's in and the set of parameters. And this just comes from the definition of the Gaussian mixture model. So first we have the Gaussian, 2 pi d. And again, we have a unit covariance, so that drops out nicely. Normally, if you were doing this with something that had more than a unit covariance, not a unit covariance, there'd be a lot more complications in the math here. Oh, that's a G. And now, there's a trick here. So we're going to look at all the clusters. That's what the J is. So I is the data index. J is the cluster. And so this is just the formula for the Gaussian. So we can find the probability of X given some theta, assuming that it's in a specific, we knew the cluster that it's in. Now, we're going to do a little trick here, and this is a little something that you'll see quite a bit. We said that delta is always an indicator function, meaning that it's only going to be one, you're only going to be in one cluster. So for a given data item, it'll always be a vector of zeros with one entry that is 1. And this allows us to do a cool thing where we can just say, take this little thing and take it to delta ij. Now, we know that delta for a given data item is only 1 in one case. So this product actually is basically, this is selecting a single Gaussian when you take this product. Because it's going to be a bunch of, when you take a bunch of things to the power of 0, it's going to be 1. And then you take a bunch of the products of 1, 1, 1, 1, and then one non-zero one, or one non-zero expression, you're going to get that non-zero expression. So this taking a power to something when you know that it's only zeros and ones is kind of a way to select out the particular Gaussian. And it's just it's a technique you're going to see occasionally when we go through the math in the future too. So we have another equation. This is the probability of a cluster assignment given the current or given a theta. And this is just the mixing probability. So in the chance that a thing is, any data item is in a particular cluster, we define that as the mixing probability. That was sort of the way that we defined the problem in the first place. So these are just the mixing probabilities of the different clusters. And again, we're going to take this to the ith j entry, and that's just the shorthand to be able to get rid of or write it in a concise way. Okay, so we'll keep going with equations here. We got to look at the probability of x I, the data item xi, and the joint with the cluster assignment given theta. And this is just the probability of xi times conditioned on the cluster assignment and theta times the probability of a cluster assignment given theta. So that's just a chain rule in probability. We can take out we can pull out this delta into a separate probability, and then we can take these two statements, and I'm going to try to write when necessary the formulas that we plugged in. So in this case, we plug in formula 3 and 4, this guy and this guy, and we end up with, let's see if I can get this right, square root of 2 pi to the dth times the exponential. This is just going to be what was up above and then rearranged just a little bit. It's a U. And then that's a delta. Okay, so we just took these two formulas, we put them together, and then we rearranged, basically moved the products around to get this formula. Okay, so now we want to look at the loss. We haven't talked about what the loss was. I think we wrote it down the other day. But the loss is going to be equal to, and this is the loss of theta given the data, all of the data, and a setting of delta. And this is just a sum over the log of the probability of a single data point, a cluster assignment given theta. So the loss, we're just going to use the log because it's going to make it a lot easier. Remember, we're just going to minimize this whole equation in the end, and the log turns all the products into summations. So it's going to make it all easier to work with. We almost always use a log space when we're talking about loss. And then this guy is just equation 5, which is why we went through the pain of defining this big guy to get that. Now, once we take the log and we push it through this particular thing, we can write it as a double summation of 1 minus, I'm going to get really tired of writing all this out. I suppose you guys have to also, so. J plus log of the mixing probability of J times delta Ij plus K. So we basically push the log through this expression, and it comes out to this. And then you'll notice we dropped this particular, the 1 over square root of 2 pi delta, and we just put plus K in the end here. Plus K is just going to say there's some constant that that's going to ride along. It doesn't matter what that constant is. It will not affect our minimization. That constant will change in each of our steps, so it's not the same constant even. But you'll end up in the end when we take the minimization, we're going to take a derivative, and that constant will just drop out. Got a question back there? I probably can. How's that? Perfect. Thanks. So basically, we put the K there just to get rid of a bunch of stuff that we don't care about, and it's just easier to write down the whole thing. Now we're gonna do a trick, and we're going to write this, I want to get the right one, this whole thing right there, we're going to form a big vector of all of the possible settings over all the clusters of this particular expression. And we're going to call that vector Ci. So for each cluster, we're going to have an entry in Ci. So basically, this is a big, is going to be a big vector, and it's going to have the one for the first cluster down to the kth cluster of this expression right there. If we do that, then we can do a nice little trick here to make this far more concise, where we take the summation of I, which is, of course, all the data, and we say Ci transpose delta I. This is the delta specific to the ith data item, and then our plus k. So we just collapsed, basically, we pushed the summation, we moved the summation around, we pushed it into basically a vector dot product, and it's way easier and more concise to write out. All right. All right, that's the first page. There's only 13 equations, so this should go pretty fast. We're up to halfway here. Also, I numbered equations kind of funny. So we had equation 6, and now we're up to equation 8. So ignore that. This is equation 8. This is the Q function that was defined through EM. And we're just going to plug in the different things we need for the Gaussian mixture model specifically. Yes? I can try. It's going to get... Are you just having trouble copying it all? Okay, yeah, let me know if you... I know it's a pain that I'm left-handed. It's far more of a pain in my life than in yours. But, yeah, I realize that I have a tendency to cover it up as I'm writing. Okay, so, we're just going to write this out. This is just the original definition. It's the loss with respect to the data and a cluster setting times the probability of the cluster setting given the current theta and the data. And this is just an expansion of, this one is literally, try to use the same, this is just a rewrite of equation 1. No, there is no number 7. Yeah, that's what I said. I had some problems. There actually was an equation 7, but it turned out that it was defined in the book for some reason, and then it was never used. And so I just sort of dropped it. And then there was an equation, I think there's an equation 9 the same way, that it just wasn't useful for, I think there was a secondary process that showed how you can move some of this stuff around that I ended up skipping. So just the numbers are going to be the way they are. Let's just pretend I can't count. Okay, so I'm going to skip a huge amount of work here. And it's in the book, but it's not particularly important to look at it. So if you want the details of how you got from this first statement to this statement, you just have to look in the book. No, that is not a K. That is an X. And plus K. So basically, we plugged in the loss from up in equation 6. This guy was equation 6. We plugged in the probability of delta given, oh, I don't even define that yet, have I? Where'd that go? Why don't I have that? Hopefully that wasn't equation 7, because then we're missing equation 7. Pretty sure I had that. Probability. Okay, we might be missing an equation then. Equation 7 is very important, and we took it out. We'll have to look in the book for that definition. We actually, you notice, okay, I know actually, it's we're not going to need it for a second. I didn't actually expand this. So basically, you go from the loss, you do some rearrangement where you you push the loss in and then you switch the summations. And the logic of why you can do that is in the book. But what you end up getting is the summation over all the data points times the possible settings of delta times the CI delta I times that probability that's right here. And we're actually going to define this below, and that's why I don't have it yet. Some of these things, it was a question of whether you put them up front before you knew you were going to need them, or you put them after, and then you're defining stuff that you don't know yet. So we can rewrite this one more time, and we get the summation of I times the summation of the delta settings for data point I. And then we're actually going to expand out that little matrix formulation, this little CI. We're going to expand that back out to its definition, which came from right from equation 6. So that comes. Get kind of tired of writing this particular thing. Plus log of the mixing. And then we're going to pull a little trick here. We're going to take basically this particular delta and this guy, and if you take those two things and you push this summation through basically to this point, you get back an expectation over the different settings of delta. So this is the expectation over the probability of the different possible settings given the current, sorry, this got a little small at the end. So it's the, wow, I'm lopsided. There you go, guys, go a little less falling over there. So that's just an expectation over the deltas, basically over all deltas. And this is going to be called, this little expectation is going to be important. That's going to be called Wij. Essentially, it's a weight that each data item being assigned to a specific cluster is going to have. So just like when we did soft k-means, we had sort of a weight that said this point is in multiple clusters. When you take the expectation over all the possible cluster assignments, meaning the delta ij's, you end up getting kind of a weighting of where all those clusters, or where each data item is going to go into which cluster. So we can define that expectation. This guy is going to be formula 10. We're going to move forward. We haven't defined formula 10, don't worry, we'll get there. Formula 10, obviously. So this is Wij. Now this is the expectation over the settings. Yes? Oh, do I? Let's see. Oh, okay. Yeah, I do. There's a bracket right here. And there would be one more bracket around here. Sorry, I really ran out of space there. There you go. And we pull that constant along. That constant just comes along.
So for the last part of the equation 8,
yeah.
Is the
This is the no. It's what the expectation is taken over. So it's the expectation. I mean, when we write it out down below, it'll actually be you take just like an expectation. You take a value times a probability, and a value times you sum over the value times the probability. That when I write an expectation like this is just saying what distribution we're taking the expectation over, because there's a lot of different deltas that we could have taken the expectation over. We could have taken the expectation just to the thetas, or we could take both the thetas and the x.
So at the beginning of equation A, is that theta j or is it theta some column?
The
At the beginning of equation A.
oh, it is a j. No, wait. This is completely wrong. This is just a j. I apologize for that. That actually, when we did all the rearrangement, we actually got to drop the delta. Basically, when we did that that vector dot product, and we pushed all of the logic of the deltas out to the end here, we can just walk across all of the clusters. So we don't have to walk across a specific delta.
But before we expanded the equation, it's some column, right?
This guy's actually correct.
At the very beginning. Is that q with respect to theta and left of the equation?
This guy.
Yeah. Is that semicolon or j?
That. Okay, so I fixed something that was completely not you weren't asking about. That's a semicolon. Yeah, that's usually read as a given, even though it's not a probabilistic statement. So usually you would say theta given, and actually I skipped the x there. So it's the Q function is always theta given the current theta and the data itself. So Wi is this statement right here, and this is a expectation over specific settings of delta. Now delta for any given, notice that this is both the expectation over both the cluster and the data point. So we're only talking about a 1-0 binary choice here. It's either for a given data point, a given cluster, it's either in that data, or it's either in that cluster or it's not. So we can take this expectation and we can find it to be the value of 1, which is it's the sum of the values times the probability. So this is the probability that delta ij is equal to 1 given the current parameters and the data, plus 0 times the probability that delta ij is equal to 0 given the current parameters and the data. This is nice because it drops out and you end up with just the probability of delta ij equal to 1 given the current parameters and the data. And this is going to be defined in equation 11. Equation 11 is the probability that a given delta ij is equal to 1 given the theta n and the current data, which is equal to the probability that the data, the joint probability of the data and delta ij is equal to 1 times n over the probability of x given the data, or given the current theta. That's just by the probability laws. We can move those around. What's up? I didn't realize that we ran out there. Okay, we'll give you a second there. So again, it's the probability of a delta ij being 1 for the current theta times the current theta and the current data, and it's just through the probability laws we can move this around to move the x over, and then this is going to be equal to the probability of x delta ij equals 1 given theta n over, and then we can just take the, we can marginalize that x out again. So this is the probability, sorry, we're going to marginalize out the delta. This is the probability of x of the joint, x and the joint delta given theta n. That's another trick you could play with the probabilities, where we take the probability, if we need the probability of x, we can take the joint of x and delta and just marginalize out a delta. Wait, there's an L there that I got wrong. This guy is L. So this summation is over the clusters. And then you marginalize it out for all of the different clusters. And there is one more thing we need to write. Unfortunately, I ran out of paper on that particular. So this is a continuation of 11. How is that different? Wait a second. Sorry, my notes. Oh, okay. We can, since we're only talking about the ith data item here, this is all of the data, but there's independence, so we can write this to only care about the specific data item we're talking about. So here we're talking about all data, and down here we're going to talk about an individual data item equals 1. So really all we're doing is changing that x into the uppercase x into the lowercase data item x. That equals 1. Data n. There we go. Now these guys, both of these probabilities, you'll notice that they're the same thing. I screwed up the L again. This is delta IL, because we're marginalizing out across all the delta settings, all the clusters. So this particular thing is the same in both the top and bottom. It's just the one has the summation and one doesn't. That's going to be equation 12. Now, equation 12 is here somewhere. If it makes you feel better, it took me about twice as long to write the notes for this lecture than it did to present it. It is to get them all right took a long time. Immediately I made a mistake there. So this is the probability of the joint between a data item and its assignment to a particular cluster, which we're going to need right up here. And that is equal to the probability of a given data item given its assignment to, or given that it's in a cluster and the theta n times the probability of delta ij equals 1 given theta n. So we just broke apart that joint probability right here into two pieces. This part right here is actually from way back in equation 3, and this guy is from equation 4. So this, we're finally using equation 3 and 4, which we defined way up here, this particular equation and this particular equation. Now, we used it here also, but we're going to use it down below. And so that becomes this is just plugging in the equations again. So this becomes, ooh, did I line up the, yeah. It's just that probability, this is basically the probability of the Gaussian mixture, a single Gaussian for a given cluster mean and the data point times the mixing probability for that particular cluster. And then we're going to continue, actually, equation 10 here. We're just going to keep writing onto equation 10, where that equation 10 was the Wij setting, and this is just going to be equation, because I'm really lazy. So it's just this big expression over this big expression with the clusters set to L instead of J. So essentially, that's the weight. You calculate, when you want to find the weight of where each data point is going to go into clusters, you end up calculating this expression for each possible data point and each possible cluster, and then you come down here and you take basically for a given data point and cluster, you take this expression over the weight of all the other expressions. So really we're just taking the weight, an average of all the weights, an average of all of these particular things. Or sorry, sort of the proportion of all of these settings over a given one. And then that ends up, why don't I find this again? Oh, I know why. We end up with, we're going to rewrite an equation, just the Q function. And the only reason I'm going to rewrite this is I want to make it clear what pieces are moving and what pieces are moving and what pieces belong to this and what pieces belong to this. So this is the double summation over the X data item, the jth setting of the means times the X data item, jth setting of the means. Let's close it out correctly. Plus the log of the mixing probability J times Wij, and we're going to put a little n there, plus k. So this is just a rewrite of the Q function that we had up above. The important thing is that this Q function is a function of some new theta that we don't know yet. So theta there is the variable of the function. This theta is the current setting. So that's actually some fixed value that we know. And when we look at this equation, these guys, oh, sorry, there you go. All of those guys and this guy, those all belong to the theta, meaning that those are all the free variables that are part of theta. Whereas the weights are all part of theta n. So calculating those weights, we only need to know theta n. If we know theta n, we can calculate those weights. Then this part is the part that we're going to actually have to use to maximize everything. So let's put that down. Try to keep that up. So that's basically the E step. That whole big mess is what we call the E step. And in the end, you'll notice we actually went from an expectation over all possible deltas, which if you think about it is an exponential sort of space. If you were to try to enumerate all possible deltas, all of the possible settings of all the possible assignments to clusters, it would get really big really fast if you had a lot of data points and a lot of clusters. So we don't want to do that actual expectation. It would just be too costly. So instead, we've rearranged all the things. We've pushed a lot of the probabilities, the math through, and we end up being able to we never have to actually look at all the settings of delta. All we have to do is calculate these weights. And then we're going to have to do something with this other part when we do the M step. So, are there questions so far? I sometimes don't stop for questions. Usually I notice you guys if you put your hands up. But, okay, cool. Okay, now we're on to the M step. The M step is extremely short. So, the M step, if you remember, is you take the Q theta n plus 1 is just going to be equal to the argmax over the possible thetas of the Q function of the theta given theta n and the data. So basically what we want to do is we want to walk through all possible theta settings, and we want to choose the one that the theta setting that gives us sort of the max of this this particular expression. Now, of course, the theta settings are infinite. They're a bunch of real values, so you can't just you can't do this directly. But we can minimize this or maximize it, depending on it's saying maximize, but we're really going to do the minimization of the negative of that. But anytime we're going to do a maximization, the first thing we should try is the derivative. Take the derivative, set it equal to 0, and see what that gives us. So that's exactly what we do here. We take advantage of the fact that the mixing probabilities over the different clusters is equal to 1. And if we know this, we can come up with the derivatives, do a bunch of rearrangement, and we actually get the final solution here. There's a couple more steps in the book, but I don't find that they're particularly informative. These become just basically the average of the weights over the total amount of weight. And those are the means. And then you need the mixing probabilities also. The mixing probabilities are also pretty simple. This is for the J. This is just going to be the sum of all the weights over the number of data points. And in the end, that's for Gaussian mixture models, those are the two equations you need to have. This guy, you need to have this, the WJ definition, the WIJ definition. You calculate that for all data points and basically all data points and all cluster assignments. So it's still fairly expensive to calculate that, but it's only n times k. Then you take those and you can find the new means and the new mixing probabilities with these, after taking the derivatives, you get these fairly simple equations. So it's expensive to do EM to some extent. But once you see the formulas, given all of that probabilistic stuff we did, it actually comes out to be pretty simple summation to find the weights, and then these fairly simple derivatives. And in the end, you'll start somewhere, you'll calculate all the weights, you'll update the parameters that go into theta, you'll recalculate the weights, you'll update the parameters, and you just go back and forth until you have a good, good solution, which is usually when the mixing probabilities and the means are not moving around too much. All right, any questions on that? That is EM for Gaussian mixture models. EM is a pretty amazing algorithm. You're going to run into it a lot if you stay in machine learning, especially if you do a lot of probabilistic work. It can solve a lot of different problems. So anything basically that has a hidden variable it can solve. But let's just do a summary, a quick summary of what we did. So we have clustering expressed with a probabilistic model. We knew it was hard to estimate. So we inserted hidden variables. And then we estimate with EM, which essentially marginalizes out those hidden variables and then re-estimates the parameters over and over. So that's kind of what we did. It's a lot of math to get there, but it's actually a fairly simple, simple formulation once you get there. We actually had one of the old homeworks from last semester. We had you write this. And I don't think we're going to do that this semester. I don't know how informative it is to make those big loops. And it's actually really slow. It turns out calculating all of those different summations and everything takes a long time, unless you are very careful to transform it into some sort of vector optimization or operations. But it's really hard to do that too. So we're not going to have you actually write that. We're going to do a different, hopefully more interesting assignment. So EM, there's a couple things. It is a general recipe. So it is an algorithm that you're going to use in different things. One example is you can do inference in the presence of missing data. So let's say you have a big data set and you have some missing entries. You can consider those missing entries as the hidden variables. Those are the things that you don't know, and you're going to try to estimate those hidden variables, basically. And depending on how you'll set up, you have to have some probabilistic framework over what you think the values are. So most likely we're going to use some multivariate normal over all the data settings. And you can use EM to basically estimate those different missing values. So that's a real common thing to do if you're missing values and you want to get them something better than just like dropping in the mean. Or the thing that we talked about previously is we could do PCA to basically impute those values. This is another way to get missing data filled in. So it's actually used pretty often when you have missing data, except that it is expensive again. You know, you end up doing a lot of re-estimates and stuff like that. We used with Gaussian mixture models, we actually had something where the math fell out pretty nicely. With some formulations that you want to use EM with, the math is just intractable. You can't get to a nice, here's some summations you have to do. And so you can actually do an approximate solution. If you remember, we were taking the expectation over these deltas. So one thing you can do instead is you can draw samples from that particular distribution and recalculate just based on that sample. So if we draw a single sample from that hidden, the distribution of the hidden variables, or a couple samples and do the summation over those couple samples, we can actually make EM work. So instead of doing all that math, we could have just sampled sort of assignments of data points to clusters. We could just, we have to know how that probability distribution falls out. But if we knew that and we could sample from it, which in general we can actually do EM without doing all the math to figure out a closed form solution. So this is actually something that is done quite a bit when you have very complicated EM. In fact, talking about doing imputation on missing data where you're trying to get the missing data value, you can just take a sample of sort of the data values. You would take literally one sample of the possible settings of the data values. Instead of trying to go through all of them in some closed form solution, you just take a sample of them, calculate the Q function, do the minimization, figure out a new set of parameters, and then sample again. So you can go all the way down to taking a single setting of the hidden variables and basically do EM with that. And there's some conditions to make it converge. You have to make sure that you're always moving in the right direction to make it converge correctly. The M step, this was basically for the E step you do approximation. For the M step, you might also need an approximation. So what you're supposed to do is do the argmax of the Q function. Sorry, X. You're supposed to do that argmax. That argmax can also be intractable. I mean, we had this nice situation where we could just take the derivative. It all fell out nicely because it was all made of summations. Your Q function might not be tractable to do sort of a true maximization. The nice thing about EM is that there's, under some conditions where you simply improve theta, you can still make progress. So you just have to have some guarantee that you're getting a better theta each time. It doesn't have to actually be the minimum theta given the current theta settings. It just has to be an improvement. And if you make an improvement each time, you will eventually converge, although the convergence rate can be very slow. So that's pretty much EM for us, and EM for Gaussian mixture models. So do we have any questions on that? Okay, so we're not going to have you do an assignment that makes you write EM, but we will likely have an assignment where you have to use EM, which is a much more sensible thing to do, I think. It's like having you write SVMs. I think some of you would argue that wasn't very informative, whereas using SVMs is much more informative for the way that they work. So we have about 15 minutes left. I want to jump back. There's a topic that we skipped. It's actually back a couple chapters in the book. But we're going to make the assignments most likely based on this topic for both 7 and 8. So I want to make sure you guys have some basis for what the assignment's going to be. So we're going to be talking about text modeling, and specifically text modeling using bag of words. Now, we mentioned this kind of offhandedly a little ways back, what bag of words is, but I want to define it a little bit better. So really what we're looking to do is, for our purposes right now, we want to have some way to measure a distance between documents. So that's kind of our goal. Now, we might be doing that to do sort of a query of the closest documents. So some sort of query where we say, okay, here's a query phrase, give me documents that are related to this. Sort of like a search engine. This isn't exactly how you build search engines, but it's somewhat related. The other thing you might want to be able to do is do some clustering of documents and sort of say that these documents are similar to each other. And then a third thing you might actually want to do is sort of do label generation. So if you had some documents that were labeled with, say, a specific topic, we could build a model that would basically, given a new document, would say it's probably likely in this kind of topic sort of thing. So these are kind of several of the steps you might use. Essentially classification, yeah. We're going to do it through something that we haven't looked at yet, but yeah, it's basically a classification task with using multiple labels. But it is a supervised process of classification, whereas clustering is unsupervised, and you're just trying to group things. Okay, so the way we're going to do this is we're going to use bag of words. Now, understanding language is very difficult. Taking a document and translating it into sort of a meaning is actually really hard. This is an unsolved problem. Like they've made some progress in processing language with deep neural networks and various things, but it's still very much an open research topic. However, we can get really far using the simple bag of words. So bag of words, basically you're going to have a dictionary of size D. This is just the words that are going to be in your vocabulary. So most often you will gather up all your words that are in all your documents, and then you'll just have some cutoff where you say, I'm not going to have any words past 10,000, that don't happen in the first 10,000. So it is a fixed dictionary, basically. And then we're going to represent a document just using bag of words. So if we have a specific document, it's going to be something like 0, 0, 37, 11, and it's going to be a vector, a column vector. And these are going to be the counts of the different words in your dictionary. So the dictionary is going to be ordered, so you know which words are in which positions. And these are just the counts. So this is the count of, let's say that's elephant, and this is, I don't know, trunk. Seems like those two things would go together. And there's going to be a bunch of other words that don't exist in this particular document. So this is classic bag of words in a vector formulation. Couple things you're going to do is you're going to ignore I forgot how to spell. Ignore stop words. Stop words just refer to words that are very, very common and uninformative. The, and, not even are going to be stop words that you're just kind of throw out. Not is kind of a hard one. You can change the meaning of text by including not, but when you're doing bag of words, you don't know where all the nots go, so you don't really know what the meaning's changed. So that's a big problem with this kind of analysis, is that you really lose a lot of the meaning when you can't negate particular statements and whatnot. But for our purposes, we'll still be able to say look up a document, whether it's has a bunch of knots in it or not. We'll be able to do that lookup of documents. The other thing you might do is stem words. So stemming words is just a process where you take basically the ending of words off. So something like cats would go to, sorry, cat. So you take like all the S's off, you take all the EDs off, you take all the INGs off. Basically all the tenses get removed, so everything's in the same tense. So this kind of processing seems like it should make things a lot similar because now cat and cats are the same word. It turns out that it really depends on what you're doing, and it often doesn't even matter. You can actually have problems with stemming. If you take stocks and you stem it down to stock, if you take stockings and you stem it down to stock, you're going from something you wear, well, maybe not all of you, but something some people wear, to possibly a stock like something you buy. So stemming can actually cause you some problems. So it's not always perfect to stem, which is one of the reasons we don't always want to stem. Typically, you could try stemming anytime you do sort of a text processing. You could try stemming, and you could try without stemming, and you could compare the performance of whatever your system is. It's often not going to make a big difference. So we got a couple minutes here. So let's talk about how we might query for a document. First, we're going to arrange our documents into an X vector. And these are just going to be our individual documents. We're going to transpose them. So this becomes the docs along the vertical, and the horizontal becomes the words. So this is just a data matrix, much like we used a data matrix before, where we just concat everything vertically together. If we have a new X that's a query, and this query can be basically, you're going to have, let's say you have a query of 2 words, and we might query, car and bike. So basically, you take the position of car and the position of bike, you'd set them to a count of 1, and then you'd want to find the documents that are similar to that particular query. So basically, what we're going to do is we're going to calculate the distance between every document that we have, or more specific, between the vector that represents those documents and the query document. So to do that, we need some sort of distance metric. The distance metric is just going to be a pretty standard difference metric, except that we want to make sure that it's normalized. And by that, we want to make sure that documents that are larger than other documents don't get some sort of advantage to being selected. So we're always going to normalize by the size of a document. So we're just going to take the document vector, and we're going to divide it by the number of words in that vector. And that'll make sure that all the documents get a fair shake. Otherwise, some documents would just be picked because they're larger. And if you're a larger document, you do a distance metric, it might be smaller, depending on what your distance metric is. So a real common distance metric that's a D, is going to be 2 minus basically the dot product between the first document and the second document, and then divided by the normalization factor. And that's going to be our distance metric. So in order to calculate a distance, we would calculate this particular thing to get our distance. Now, for historical reasons, we don't actually use this. What we typically use is this guy, just that thing. And this is typically referred to as the cosine distance. Now, it's not actually a distance. It's actually a similarity. So the higher it is, the better. Not the lower, which is distance would be. So you got to be a little careful to know how this works. But that's the most common thing that we use with distances, or for a distance. I don't want to get into one more big topic, so I'm going to mention one more thing we might do for normalization that is pretty quick. We talked about just normalization by the counts, but we might also want to be careful about words being too common or more common versus words that are less common but more informative. So if you have a word that occurs all the time, so let's take one of our stop words, the. The is going to be in every document. It's going to have high counts, and it's going to be very useless for any kind of discrimination, a query, or any kind of system that you want to process text. If a word exists everywhere, it's not informative. And so conversely, if a word only exists in a small number of documents, it's probably very important for those documents. So if you're looking for something very specific and it only occurs in a couple documents and you query for that specific word, it's going to get exactly the documents you need because it's such a rare word. So we'll often reweight our counts of words, and instead of using the counts, we're going to use something called TF-IDF, which is term frequency inverse document frequency. So this is going to be TF-IDF. Instead of using the direct counts, what you're going to do is you're going to use basically the original count of the number of times that word appears in the document. And then we're going to take it times the log of the number of documents over the number of times or the number of docs that term occurs in. So this is num total docs. And this guy is num docs with words. So if a term occurs in every single document, it's going to basically it's going to use just the count. But if a term occurs in very few documents, this count is going to be multiplied by some much bigger number. So that count will be basically increased quite a bit. Now you're still going to do some normalization over the counts, the length of the document. But those terms that are important, the words that are important, are going to get a big upscaling. And this is used, this is standard search engine sort of thing. Now there's other ways you could scale them, but really all that matters is that you make the rarer words much more important. And that's going to be done in basically every search engine, every query, anything, any kind of word clustering. You're going to do this sort of thing as just a standard first pass sort of thing. On Thursday, we'll do a little more of the text processing, and then we're going to actually move on to regression, which is a whole nother topic. So I'll see you guys on Thursday. Is there a question?
Real quick, what's CIG?
That's the, sorry, this is the original counts. So this is the count of word I in, word J in doc I. All right. See you guys on Thursday. Yeah, sure.
So it's about the homework for report. Let me see if I can make this bigger so you can see. Just like type it. Okay. So my distance matrices, they're correct, but I just wasn't sure if I'm getting these values, because remember you said sometimes you square it and not square it when you send it to PCA. Is this range looks correct to you? Well, I can see the clusters going like the animals.
You know, I haven't actually looked at the answer, and even if we actually talked about this the other day in our TA meeting,
Right.
A lot of people are asking, does this look right? So, short of what we recommend is that you test it on some small thing where you kind of would know what the layout would be,
Right.
and you can kind of look at it. But short of that, I can't look at this and be like, yeah, that's right or that's wrong. There probably is a correct answer, but I just don't know what the layout's going to be.
No, I'm saying in terms of grading, would you be picky over the range and stuff?
I don't think the range matters.
Matters, okay. So
It's
it's just
more
more
of
like
the
a relative.
layout. But I'd have to look at the other submissions to see if really what we're going to do is we're going to take all the submissions and make sure they kind of all look the same. And if you're a outlier who looks completely different, we're gonna dock you points. But I haven't looked at all the solutions.
That's
So
the reason I'm asking is like, remember you said like if yours completely goes wrong, we can go do a 7A and like.
yeah.
But if I kind of like, this is 25 points for this. If I kind of like, no, this is not.
Yeah, I unfortunately I just don't know what it should look like. We recommend that you test it on just a small piece of data and
With
see
the
what
test
happens.
case that they provide for the CRF, they have like the default version for Python.
Yeah.
They have 5 data sets and one with the labels and one test data, like test data sets. That helps here to do anything with like checking
You have to know kind of how things will fall out when you have your test case. Like you should need to know, you have to know, yeah, this is kind of the right solution that I should see, which makes it coming up with test cases kind of hard. So I'm not sure about those particular data sets. There's been some Piazza posts about this, and you can go through them and see if you can suss out whether this looks correct or not. Unfortunately, I just don't have a good answer.
I didn't expect you also to get
Yeah. Hey, what's up?
I just have questions about like what each variable means and like the notation.
Yep.
So like what's the difference between having a semicolon and having just a bar?
Again, this is a probability versus non-probability. They're both pronounced given, but if you have a probability, that means that given a setting of these, all of the settings of this have to add to 1.
Okay.
So it's a probability distribution, meaning that they have to sum to 1.
Okay.
This guy, the reason we use a colon there and a colon here is because these guys will not sum to 1. They're not probability distributions. And you can actually look. It's a sum over all the data, or actually in this case, all the deltas. So there's nothing to, okay, this is an expectation. This expectation, we don't care about the expectation. We're actually looking for where's the L run off to? It should be down here somewhere. This guy. So this guy is over all the data points of the log of some probability. So this would sum to 1 if you had all possible settings of data points. But if you take a sum of a log of a probability setting, this thing is not going to be 1. It's not going to sum to 1 if you had all possible data. So that's really the difference is when we do P of a given, there's a specific meaning of that, meaning that's a distribution. If we do log of this semicolon, that typically means we're not talking about a distribution.